class. So a couple of things that we will do today. I will continue the lecture from last time and talk a bit more on file organization. And today we'll introduce different data structures for that. Okay? And thank you guys for being here. I know a lot of people are already traveling somewhere else right now. So yeah, good job. And let me see. Just want to remind you, so homework 5 is already posted, and it's due the Wednesday after. And I will post homework 6 soon, like today or tomorrow, so you can work over it, but it's due the week after that, okay? And also, I think the TA hasn't sent out the email for scheduling the demo, right? Okay, I'll tell her again, and you guys only need to settle that down by the Wednesday after the break. Okay, so this demo will happen Thursday and Friday after you come. All right? And then for our final presentation, it's actually coming really soon, and I plan at this time to do it in class. Okay, so you don't have to go out for the other than class time. So we'll do it in class. Okay, and that will actually take up to 2 classes. So that will be for the final week of lecture. So the week before final week, the Wednesday and Friday we'll be doing presentation for our final presentation, final phase. Okay, and today the lecture will be a bit shorter because I want to give you back your midterm 2, part 2. I was going to give you back part 1, but he is still grading it. Okay, so I'll give you the part 2 first. And if we finish the lecture early, you can talk to me if I took off any points wrong. All right, and I'll also show you what your performance is, like where you're at in the class, and so on. Okay? All right, so let's get started. So last time you remember, we were talking about different kind of file organizations, right? In a few lectures before, we were talking about different kind of alternatives for indexing, for connecting the data entry to your data records. Okay. So to review a little bit, last time we talked about hash-based indexes. Okay, if you remember. So basically, for hash-type indexes, which will be part of the implementations you need to do for your bonus for homework 5, if you're very interested. So hash-based indexes, basically, this is just one example of it. It's not like every hash indexes is this structure, but you can take a function that we call it the hash function, taking the parameter, and then output different results, direct you to different buckets in the hashing based on your hashing function. So last time, we were working through the example where we took the parameter or whatever input we say, and then we convert it into binary and we look at the least 2 significant digits. And then that directs us to different buckets. All right? So for buckets, we say that are the location where either the data entries are stored, or you can directly put data records if you're using alternative 1. Okay? And for buckets, every one of them has their own capacity. Okay? And last time we talked about what will happen if the capacity are exceeded and we still want to put in more data. So last time before we finished the quiz, remember the first question I asked is, what is this? And that's the bucket, okay? Someone answered it. And we say if we want to add a bit more into that, we put overflow pages, right? If you remember that. All right? So in this example we worked through on the blackboard last time, we say, so the data are not shown on here, but we say for right here we can use alternative 1, so which is the actual data records are stored in here. But for this one we can just put alternative 2 or 3. If it's alternative 2, we only put, for example, the RIDs that are directed, right? Directing to the data records. And RID, if it's alternative 2, then it's one RID mapping to a 1 key mapping to a 1 RID, and if we use alternative 3, then it's 1 key mapping to a list of RIDs. Okay, and if you recall last time we actually say in this whole structure when you're designing it. So again, this is not the only way of doing it. Okay, so when you're designing it, remember if we already have one alternative 1, you don't want to have another one. And the reason being, alternative 1 already have the data record stored in there, so you don't want any redundancy. If you have more than 1 copies of alternative 1, then you're actually just storing duplicate data records. Okay. So that was for the hash-based indexes. One of the 2 parts you're using for your books. Okay. And last time we quickly talked about what would happen for tree-based. So tree-based, last time we just quickly brushed through. There's this one structure right here. We can use an index file that will direct it to data file. And data file are broken down into different pages. Okay, and we use the key to tell us which data file we want to go to. And last time, at the end of the lecture, we say, for example, in this example, for K1, it means the pointer on the left side of K1, it points to the pages where a certain attributes are all smaller than K1. And for the pointer, this is actually between K1 and K2, okay? For the pointer between K1 and K2, it points to the page 2 where a certain attribute is between the range of K1 and K2. And then for here, page 3, we're saying then it's greater than K2. And last time we were talking about why we would want to use this tree-based kind of structure. Okay. Another note is here, we are already assuming that certain attributes that we want to compare against with the keys are already sorted. Okay. So why would we want to use tree-based? Any idea? So tree-based can make you kind of relate to this order of the attributes, right? Like I said here, maybe we have a certain key, certain attribute which is easy to compare with the key. So if you think of it with compared to the hash-based, in hash-based, because of the hashing function, so a lot of times when you want to do a range query, it will be a lot harder because even though we say doing a hash function, the complexity of doing so is just constant. Okay? Just compute it and then you go to the direct bucket you want to go. But today, if you want to say, I want to get all of the data where the attributes are within a range, then working through the hash function actually won't be efficient because instead of just saying, I find a starting point and then I go to the end point, you actually have to compute every possible values with the hash functions. Okay? If your hash functions cannot relate to any range of information. So this is why tree-based will come in handy. And right here, we only show you where this is just one level. Okay, so it will actually really come in handy when we put this in the repeated way, when we build up levels. So it really looks like a tree, okay, which I'll show you soon. I'll draw on the board. So if you take a look at next slide, for this kind of one type of the tree-based structure, we actually call it ISAM. So ISAM stands for, I forgot to put it on. Stands for index sequential access. So by the name of index sequential, you know the way they structure, the data structure will have the index sorted in a sequential way. So what exactly is ISAM? So later on I'll come back to this, but just like we said earlier, in the previous graph, you see different keys, right? The K1 and K2 are the keys. And on their both sides, they actually have pointers that point to the pages. Okay, key on the left side point to the pages, and on the right side also have pointer pointing to the pages. And that's the basic building block of such tree. So let's see how we can actually construct an ISAM tree. So one of the very important concept in ISAM is that you want to think of each node Later on we'll talk about the node in the tree, each node in the tree, each node in the tree. Is a page. Okay, I think I didn't write down for the slides. But later on you'll see in the tree structure, we will want to view them as the unit of page. Okay, so say today we have a bunch of data that we want to store, and we want to store them, access them based on certain attributes. Okay, so I think these will be shown. So I'll just show you how they're actually constructed, but the example is actually on 12. No, page 8. Okay, so that's what we are going to construct. So say today we already have a bunch of entries that we will use to enter the data records. Okay, and now we just sort the entries by their values first. So if you look at the slide on the very bottom part, okay, so I'll show you. Okay, so they're already put in order. Okay, so just remember again, these are the data entries, and they're actually used to direct to data records. Okay, data records are actually where the informations are, but entries are what is used to refer to the data record. Okay, so can anyone tell me why on the top right position of each value we have a star? Do you remember? If you recall, I think 2 lectures ago, we talked about if we put star, it just means it's data entry. Okay? So that's why we have that. Just to differentiate between just normal values, or maybe that is used for data entry. Again, data entry, what they are for. What are they for? They are for going to data records. Okay? And so in this example, now we have all these data entries right here, we sort them. Okay, so remember the thing we're doing now is to build the tree. So it's a file creation part. Okay, and the assumption made here is each page contains, you can say 2 values or 2 something. Okay, so here we have the page unit, the capacity being 2. So what you want to do, because here we want to construct nodes, or we want to do it bottom up, so we pair them up 2, 2 together. Okay? So that's how we pair them up. So now you can view each pair as a node. Okay, so once this part is done, we call them the leaf in the tree. So if you have learned about data structure before, actually the roots are at the top, the leaves are at the bottom. Okay? So that's the first thing we will do. Okay, you start it out by sorting the data entries, pair them up based on the unit you have for your page, okay, and then here's the leaf part. And it's done. So then, now you will see the tree actually has 2 more levels, okay, on the slide. So what are they? What they are for? So let's say today we already have the fact that each page contains 2 values. So earlier you see we have this structure of pointer, key, pointer, key, pointer, okay? So what this is just the building blocks of how the keys and pointers are used together. So when we have a key K1, then the pointer P0 on the left points to the pages where the values are all smaller than K1. And for P1, it means the values between K1 and K2. And then for P2, it means all the values pointed are greater than K2. Okay? So, right here you see we also want to add in on another level, on top of the leaf level, other pages, which are other nodes, right? So we take a look at here, if we say each page can only contain 2 values. If contain 2 values, how many pages can a pair point to? 3, right? Because 1, 2, 3, and we have 2 values. So right here, it just happens we also have 6 pages at the leaf. So we know for this upper level, we need 2 pages. Okay? So you draw that out first. Okay, the center one I'll use as a pointer, and then here's the key. Okay? And what you're going to do first, before we fill out the value, we know for this page, it takes care of pointing to this 3, and the second page, it points to these 3. Okay? So how are we going to fill out these values? So we want to say for everything that this pointer is pointing to, we can think of it as the P0. Okay? It means it's smaller than values here. Okay? So the easiest way for you to do it is just take this value and then put it up there. And for sure, all of them will be smaller. So you can put 20 right here. Okay? How about this one? It has to be between the range of these values and these values. What do you think? So an easiest way, take this. Okay? So we can do this one goes up, this one goes up. Okay, how about here? Then again, do the same thing. We have 51 right here, and then we have 63 right there. Okay, so for the second level, now we can see, really easy to see, the reason we have them is for indexing. So the pointer points to here are all smaller than 20. So if you want to find a values that are smaller than 20, you will go here first. Okay? And every tree starts with the root, but now for this level, we still have 2 pages. So we want to go up even further to build one more level to make it the root of the tree. Okay? And because this time we only have 2 pages in this level, so we only need 1 for the upper level. And actually we won't use all of the pointers, right? Because we actually have 3 pointers. So we only need 1. We only need 2. So for a pointer, we'll fill out this value later. So we point at here, and this pointer, we point at here. Okay? So how about this time? What do you think the values of that should be? What? 51. If we put 51, and you go look at the subtree of this side, 40 is smaller than 51. So what should we put? In some sense, we find the tree on the right side and the minimum of it, right? So it's 40. So you see we have this value up there. Okay, so it's the first one. So that's how we actually construct it. So let's see. Here we have the file created. So we call it the file creation process for ISAM tree. Okay. What if today we want to insert new values? So one of the very important concepts of ISAM is that once it's created, the index won't change at all. Okay. And the number of leaves are fixed. So if today I want to add in, let's say, 23. Okay. Where do you think 23 will go? Here, right? So instead of saying maybe we should expand the page or whatever, that's where we do the overflow page. Okay? So then we add in. Okay? So you can see that will be, yeah, on the next slide, slide 9. How about 48? So 48 goes here, okay? So we also add in another page, which we call the overflow page, okay? How about 41? Same, right? It should be right here. Right here, and just remember when we add it, we actually don't rearrange it. Okay, we see a spot, we just put it in. Okay, finally, how about 42? Still same spot. Yeah.
So are these pointers that are like
yeah, they chain them together, so they are pointers as well.
Okay.
So here we have 42, and we chain them again. Sorry, this is really low. Okay? So that's what we can observe right now. If we add in new values and we have no spots left, we directly append overflow pages. Okay? So right here, a couple of important terms that we want to use. So for these that are originally created, we call them the primary pages. Okay? I think it's on your slide. And for these that we added in later, we call them the overflow pages. Okay? So for deleting, it's also very simple. For example, today we start by deleting 42. You can see on slide 10. We then try to delete 42, and we see it's just here. So we just directly delete it. But when it's actually being implemented, it might not be as easy because you want to find 42 first, right? So the way to find 42 is you go up here first, and then say 42 is greater than 40, so you travel here. And then you know 42 is less than 51, and then you travel here. So that's how you find 42, okay? And then we can also try to delete 51, okay? That's it. And then you keep going. And then, after you deleted these values that are indicated on slide 10, we will be left with some empty spots in the primary pages. Again, for ISAM, it doesn't fill the back, okay? So that's the simple implementation for ISAM. So, can anyone think of what is one of the biggest drawbacks of ISAM? One of it, when we were earlier looking at, if we keep adding values, and it keeps being aggregated right here, the chains can get really long, right? So actually, even though at the beginning, the intention and motivation of ISAM, which I'll show you later, like it's supposed to be efficient for you to find certain values, but if you chain it long enough, then you actually spend a lot of time traveling down to the chains to find the certain values, okay? Then the efficiency is not that obvious anymore, okay? But before we get into what are the other alternatives, let's take a look at the normal or common cost, or most frequent cost for traveling to the leaf. So every cost, we'll view it as an IO. So when you travel from one page, traverse from one page to another, that's 1 IO, and we call it cost of 1, we just call it 1 unit, okay? So what do you think will be the cost of going from top to bottom if we ignore the overflow pages in this example?
Ignore the overflow pages?
Ignore. 2, right? So from top to bottom, the most we need to travel is just 2, right? So we call that the height of the tree, okay? So how can we generalize this? If we have different, say, if today we change up the size of the page and we change up the number of leaves at the bottom, do you think it will still stay 2? The height varies, right? Depends on the tree. So how can we compute the height? What do you think? If you have learned about algorithm before, anyone remember how you can compute the height? Okay, so you can take a look at slide 7. There I put 2 letters. One is F and one is N. Okay. So I want you to change, for F I put number of entries. Oh yeah, that's true. Okay, never mind. So for F, I put number of entries per index page, okay? So I think that's not a very good way of putting it. Maybe think of it as number of children per index page. So for example, right here, the F will be 3, because it can point to 3 pages. Okay? So we want to represent the height in terms of F and N, where the N is number of leaf pages right here. Can you think of how we can do it? Anything?
Log S is obvious.
Yes. So it's why?
Because that's something you're screwing up each time.
Exactly. Okay, so let's work through it again. So for that one, remember I said earlier, this tree itself, actually we didn't use the most of the root, right? So if we try to recover it back, say, for the starting from the root, we already point out to 3 children. Okay, so this will be a bigger tree. And then for the second level, other than having just 2 pages, now we have 3. And then we keep expanding. Every node leads to 3 children. So how many nodes, this is kind of ugly, but how many nodes do we have for the root? We have only 1. And for the second level, we have 3. And for this level, we have 9. So you can actually think of 1 as 3, 0. Okay. And this one, 3 to 1. This one is 3 to 2. So how do you get this part? By taking log, right? Because if we even expand even more, then it keeps going on. We can get more and more and more. Okay, until the height plus F height. Okay, so right here, let's say we only care about here, how many levels we have, what's the height of it. Then we take log 3, 3 to 2, right? This 3 to 2 comes from here. So that's why we say the height is 2. Okay, but if you take a look at there, you say, but for the second level, we only have 2 pages. Okay, then you want to think of it this way from the complete tree right here. We remove this part. That's the part that we didn't think of, right? Too passionate, but so for that part, we ignore this little tree right here, right? For the second level, we only use 2 pages, even though each page are capable of pointing to 3 children. Okay? So the fact that we take out the subtree, do you think it actually affects the height? It doesn't, so the height still doesn't change. So when you want to compute, it will stay the same. So even though earlier we say, okay, the height will be log Fn, so in our scenario, that will be log 3, 6. So actually not all the way to 2, so you want to think of it as taking the ceiling of it. Okay. So then it's 2. All right? So that's how you can get the height of the tree. Okay, any question for for this one? Yeah.
So when we insert, we always insert the overflow pages after the page is done. Don't we reconstruct the page again?
Oh, we don't construct it. So for
How
ISAM,
much of our entries we keep on adding? We just add.
we keep adding it, okay? So that's why ISAM has this drawback, okay? You just keep chaining. So a lot of times, if in the end it gets super imbalanced, then every time you want to go to that point, it takes very long. So you lose the point of having the height being 2, which is really fast, supposedly. Okay. So I'll show you how to this time. So ISAM has this drawback, even though if the design is well, and if the data is well distributed, then we can see earlier that the height is so small, so the cost of retrieving the leaf is really small. But if it's not so well designed, then the chains will be really long, then it loses the point of the short and traversing time. So that's what, so these are the things I basically just said earlier. And for this part, just fill out, that's the blank there, that's log Fn. Cost equals to log Fn. That also showed you the, okay. So that's, this part I'll talk about next time, which is the B plus tree. Okay, before we get into that, I'll do next time, but just take a look at the difference. So there's not a big difference right here, okay? But you can think of ISAM as something static because the whole structure got fixed besides the overflow pages when it's created. But for B+, it's trying to compensate the drawback of ISAM. So instead of adding overflow pages, it actually keeps the tree dynamic. And between the leaf pages, they can communicate, okay? So next time I'll show you, like, if we have some empty spots, then they can actually exchange the values between them. So instead of having that awkward end result of ISAM we saw earlier, B plus that. And the goal of it is trying to keep it balanced, right? Okay, so that's for the lecture for today. And I think, okay, give me 1 second. I'll give you back the exam now, and then I'll show you the distribution. I'm not sure, I don't really think we have time to go through it.
But still the non-leaf pages won't be reconstructed, right? How much of our entries you keep adding to the B plus tree, the non-leaf pages won't be reconstructed, right?
The non-leaf, no. So they keep everything.
That is taking the machine. What if you don't have any empty space in the leaves and you want to keep on inserting data?
Yeah, so that would be still inefficient because if you go out of the range of your indexes, then that's still not good. Okay, but that will be the last result when they want to add the overflow. But if it doesn't have to happen, then they just communicate.
But how do they determine the first construction of the tree? Based on the initial set of data? Or like how do they determine the number of levels?
So that will be, the construction will be similar to ISAM, like what we just did.
Based on the initial data.
Yeah. But then the maintenance will be different. Okay? Okay, I'll just quickly show you how it's going to be like later when you get your grade. So don't worry, it looks like maximum is like so low, so that's why. Just remember part 2, the maximum is 65. Okay, part 2, the maximum is 65. And I don't know when when it renders, it goes all the way up to 70. But basically this blocks means if you are 65 points. Okay, so we still have some people like a couple points. All right. So what do you guys think? Definitely not as easy as the first time, right? I think it's not that bad. I think the average is 52. So hopefully the part 1 will be out today, so you can just add them together and see what your total points for midterm 2 is. So we have 3 parts in this midterm, And the part that performs the best, I think, is the NoSQL, which is problem 2. Okay, I didn't really ask any too technical or difficult stuff, so everyone performed pretty well for that. And a lot of people lose point in problem 1, which I think is kind of a shame because those things aren't that tricky. Okay, and if you lose point in problem 3, I can understand a bit more, like why you did it wrong or stuff. Okay, so for problem 1, the first question, I think maybe 80% of the people got it right, so the answer is cursor. But if you put API, then I give you 1 point. Okay. But I think there are other really creative questions, like super long answer, and then those I won't take it. Okay, so I know you're trying, but yeah, the answer is cursor. So that's for taking care of the mismatch, if you remember. Okay. And the second one, we are asking about HTTP. So basically, I want you to just briefly tell me what stateless means. Okay, I think everyone gets it right. Okay, just some people will put it super simple, but I still give you right. You just basically say doesn't remember anything. I'm like, okay, you get the point. Okay. And for B, what are the 2 remedies of this drawback? So I think some people might have misunderstood what I was asking. So this question is asking basically, since HTTP is stateless, what can we do to compensate that? Okay. So some of you might have answered something that is actually correct, but I gave you wrong. So the answer will be using cookies or dynamic URL. Okay. And the third one, quite a lot of you might have gotten just slightly off. So basically, I was asking you for these 3 major web formats, which ones are document oriented and which ones are schema oriented. When we talk about document oriented, we're talking about when it's getting rendered, right? Being rendered, and what web formats focus on that more. And for schema-oriented, we take care of the data structure, the structure of the relation. Right? So for document-oriented, that would be HTML, and the rest of them, XML and JSON, are schema-oriented. Okay, some of you got it wrong. And for number 4, I actually, yeah, I think I made a mistake when I made the question. So I put JSP, but I think I didn't put enough emphasis on JSP during the lecture. So some of you raised their hand during the exam asking what is JSP, and I was like, did I teach you or not? Okay. So for this one, actually, if you got A wrong, I won't take off any points. Okay. So you feel free to put JSP wherever. Okay. But it's supposed to be go to middle tier. Okay. The one in presentations here, the only one will be JavaScript. Okay, and the other one in middle tier is Apache web server. A lot of them put them at data management. Okay, but it's a web server. They're supposed to go to middle tier. And from data management tier, that will be MySQL database and store procedure. Okay. So for these questions, to make sure you can get them all right, because for the final, I might run out of time to create new questions. So a lot of times they will come from the old exam questions. Okay. And this part, I think most people got it right. So basically, and some people picked out some mistakes that are pretty funny. So for the first one, the mistake I made, no one told me about it during the exam, but it's not supposed to be a curly braces. Okay, it's supposed to be a bracket. And another one I got picked is statistics for dummies, not for dimmies. But yeah, you won't get points by picking that up. I just realized when I was grading yesterday, I was like, no one told me. But yeah, it's supposed to be for dummies. Okay, and there are 2 mistakes in this XML. The first one will be not having published information, so it's required. Okay, and another one will be not having format. Okay, some people will pick say, oh, a genre should be under book. No, right? Genre, we say it's an attribute. Okay, so this is correct, having it right. Okay, and some people think, oh, there's no first name. But take a look at here, we have a question mark here, and in regular expression, question mark is optional. Okay, so you don't necessarily have to have first name. Okay, so that's the only 2 mistakes. Okay, for NoSQL, what does NoSQL stand for? Just put not only SQL. Okay, That's it. I'm just asking you what's in store. And for here, I think the answer is fall through true. Okay. The first one of the major drawbacks of NoSQL is its low scalability. It's the total opposite. That's the total advantage of that. Okay, and these two are both correct. Okay. So for this one, it's just keep at it. Okay. When I was picking the graph to test you, I was just picking the one that shows best on paper. And after exam, I think Ujie told me, it's just right here. So it's key value, okay? This is the key value type data model for NoSQL. Okay. And then right here, actually I won't be too picky about it because there are so many reasons that people are changing to NoSQL. So if I think your reasons make sense, then I'll give you points. If I take out points because I don't actually understand what you're talking about, then you can explain it to me, right? And this part, I think because everyone has worked on the homework, so most of you got it all right, okay? So for the first part, which is this part, right, I think I numbered it in the exam. So for the first part, we're basically saying the projection. We're saying what field we want to keep, okay? Name we want to keep, weight we want to keep, and then ID we don't want to keep, okay? So some people will just say, it's just doing projection. I'll give you right. But if you start saying, well, we want to keep the name, we want to keep the weight, and we want to keep the ID, then that's the part you get it wrong. Okay, we don't want to keep the ID. The -1 means that's the one we want to exclude. All right, and sorting, I think everyone got it right. Sorting just basically sort by weight in decreasing order, and limit, we only want 2 records, and then skip the first one. Okay, everyone got it right. And for this one, correct answer is B. Okay, if you remember during the demonstration class, if we do A, then that will replace the whole unicorn information with just weight equals to 600, like if you recall. So that's for number 6. And then 7, let's see. And write down answer. Okay, for the first question, I think everyone, whoever worked on it, got it right. You just need to draw the arrows, right, pointing the functional dependencies. But some people, I think, missed the whole question, even though it's just 1 point. They just forgot to draw arrows at all. Okay, and then the second one is based on transitivity. I think almost everyone gets it right. Okay, and then this one, it's true. Okay, you can go back and take a look at the theorem, and there's one that you can check. Okay, when you have a dependency. And then you break it down based on dependency. Then we can check whether the composition itself is lossless. Okay. Number 4, the answer is B, D, E. Okay. If you have any question working it through, come to me and ask me about it. Okay. And number 5, minimal cover. The answer is C determines A and then A determines B. If you put C determines B, then that's wrong because we can't infer from C determines A and then A determines B to C determines B. Okay, so you don't want to do it. All right. Then that loses the whole point of minimal cover. Okay? So the final one, okay, after I just quickly talk through it, I'll let you go. Some people get 1 point off for each part. That's because right here you're supposed to put the functional dependencies. Okay? But if your decomposition is right, then you get it all right. Okay? So a lot of people make mistakes at the second normalization. So you also break it down of the phone determining average. Okay, that is the part you only have to do in third normalization. Okay, think about it because of the partial dependency. Okay, so I'll post the solution later on. Maybe I'll work through it during the break. But just remember, for initial design, it's a big table. Second normalization, we'll get 2 tables. Okay, and then in the third normalization, we get 3 tables. Which I'll post it on AIM. So you can check if I grade anything wrong, let me know. Okay? So that would be it. I'll see you after break, and don't forget to work on homework. Be safe. Okay? Yeah.